Hi, in this video we'll go over the effect of diversification, which is the end stock situation here. So we have dealt with 2 stocks, 3 stocks, and we've been using the covariance and variance matrix to calculate the overall variance or the standard deviation for the portfolio. But what if we have so many different stocks and each with different weights and individual risks? How do we come up with a conclusion on this particular portfolio's risk and return? So it's nearly impossible if we have n stocks and each stock is different here. So we need to make simplifying assumptions here. So since we have n stocks here, why don't we assume that the weight for each stock is the same, which is going to be 1 over n. So it means all the stocks in this portfolio are equally weighted. Okay, they're equally weighted, so it's 1 over n. We can further assume that the standard deviation or the risks for individual stocks are also the same across all different stocks here. So sigma I here is equal, let's just call it sigma here. Okay, and then we still need the correlation coefficient for all the pairs of the stocks. And let's again assume that all the pairs of the stocks return would have the same correlation coefficient. So rho ij, for any I that is not the same with j, is going to be rho itself. Right? So with these 3 simplifying assumptions, we can come up with some conclusion and a bit of calculation steps for this portfolio with n stocks here. Okay, so we're still going to use a covariance variance matrix, and we're going to lay it out nicely like this way. Okay, but we don't have to, or there's no way for us to write n stocks here, so we're going to just skip some of those. But we'll use a few of these stocks as the indicators here. Okay, so for the first term here, that's going to be our first stock's own variance with its weight squared. Right? So since we know the weights are the same across all the stocks, and the variances or the standard deviations for each of the stock are the same, so we can confidently write this part as 1 over n squared because of the weights here. Okay, so W1 or W1 squared, and then sigma 1 squared here. Right? Okay, so since every stock has the same individual standard deviation, we can just drop that 1 over here as well. So it becomes 1 over n squared and sigma squared. Right? And then let's take a look at the diagonal positions for this matrix. Okay, so on the diagonal here, everything is just variance, or the variance for the stocks themselves. But remember not to drop the weights here. So on the diagonal, I can write everything is just 1 over n squared times sigma squared. Okay, and for the third stock as well, so 1 over n squared and sigma squared, all the way to the last stock here. So it's going to be 1 over n squared times sigma squared. Okay, so now we need the rest of the parts, or rest of the terms here. So what's going to be here? Okay, so it's going to be W1, W2, but since they're the same, they're still going to be 1 over n squared. Okay, now we have rho 1, 2, sigma 1, sigma 2, and since all the sigmas are the same, we just need to include the sigma squared and the rho here. So rho times sigma squared. Okay, so the same for the symmetric positions here, right? So 1 over n squared, rho sigma squared. Right, let's take a look at the term between the first and the third stock here. So W1 and W3 still the same, sigma 1 and sigma 3, they're still the same, and rho 1, 3 is the same as rho 1, 2 here. Okay, so we can still confidently write 1 over n squared times rho times sigma squared. Okay, and as you can see, all these terms here, as long as they're not on the diagonal, they will remain the same. Okay, they will be the same as 1 over n squared, rho squared, and sigma squared, and except for the diagonal here, which is the variance of the stocks themselves. Okay, so the portfolio's variance is when we add all these terms together. Okay, it might seem a little bit daunting here, but we can collect so many terms so that the conclusion here, or the result here, is going to be very clear. Okay, so let's first pick up the diagonal here. So how many terms are there on the diagonal? There will be n terms because we have n different stocks. So there will be n variances here. Okay, so on the diagonal here we have n times 1 over n squared and sigma squared. Okay, and these will be the variances, and then plus all the remaining terms. Okay, all the remaining terms, which is any term that is not on the diagonal here. So how many terms are there if they're not on the diagonal? So since this is a variance covariance matrix, there will be in total n squared terms, right? We have already considered the diagonal here, which consists of n different terms. So the rest of the terms must be n squared minus n, that many of terms, right? So n squared minus n, and then each of these terms are identical. So that will be 1 over n squared, rho, and sigma squared. Okay, so that is going to be the variance. That is going to be the variance of this whole portfolio. But can we simplify it? Yes, we can. So let's keep the relative structure here. So this bit is the diagonal. This bit is what is not on the diagonal here. All right. So for the first part, let's just eliminate this n here. It becomes sigma squared over n, right? And then plus here, we can write the n squared minus n in another way, in a different way, which is going to be n times n minus 1, and then divided by n squared, and keep the rest. Yeah, we keep the rest. So since we have n here and n squared here, right? So we can cancel out one of these n as well. So it becomes, finally, as the result, sigma squared divided by n plus n minus 1 divided by n and rho and sigma squared. Okay, so this is going to be the result for our simplification for the variance for the portfolio here. But as n becomes significantly large or goes near infinity here, or n is sufficiently large here, okay, so this thing can be further simplified. As you can see, we have n on the denominator for the first term here. So if n is sufficiently large, this thing is going to be very small. So small that it's close to 0. But this thing here is not going to be 0. That's n minus 1 and n. So this is going to be very close to 1. So think about n is 1 million. So this is going to be 1 million, and this is just 1 under 1 million. Or alternatively, you can think of this as n is 1,000,001, and n minus 1 is going to be 1 million. So 1 million divided by 1,000,001 is very, very close to 1. Yeah. So this bit will be simplified to 1, and this bit will be 0. So we can have the final result here. If n is sufficiently large, then the variance is going to be rho times sigma squared. Okay. So how do we interpret this final result? Since the rho is the correlation coefficient that strictly stays within the range of -1 and +1, yeah? So it's going to be less than 1 or and must be greater than -1. So in very extreme cases, I'll be exactly 1 or exactly -1, but it's very rare here. So theoretically, this thing here is going to be at least the same as sigma squared, if not smaller, right? So if rho is strictly less than 1, then this thing is strictly less than sigma squared, right? So we can move this thing out here. So it's going to be strictly smaller than sigma squared. So it tells us with n stocks here, our variance is going to be strictly less than by holding the stock itself. So we can say that this sigma squared is the variance of the stock itself, right? So with diversification, with reasonable diversification here, and in a very extreme case in which we have here is that everything is basically the same, we have a final variance that is smaller than the stock's variance itself. So it sort of tells us the more we diversify, the less the risks, right? So we call this the power of the diversification here, okay? And then we can further conclude that, let's take a look at this part here. this is basically the average of the variances, because that's sigma squared divided by n here, right? So we have the sigma squared divided by n. We call it the average of the variances of the stocks, right? Of stocks, or individual stocks, right? Individual stocks. And as we can see here, as n goes up, this thing goes down to 0. So we're basically diversifying this part of risks away, right? So that can be diversified away. So sometimes we also call this part as the idiosyncratic risks or individual risks. Idiosyncratic risks. But this part, however, you cannot make it 0, right? You cannot make it to 0. Though you can argue if rho is 0 here, then this thing goes to 0, but it's very unlikely that everything in this market is unrelated. So we can sort of assume that rho, even though it can take the value between -1 and +1, it's going to be somewhere that is a positive. Yeah, that is positive. So it's not going to be diversified away unless this market is completely uncorrelated, which is not going to be the case. Okay, so the next part here, we can give it a name here, which is the systematic risk, or the rho sigma squared. Okay, let's use another color here. The rho sigma squared this is not going to be diversified away, so it cannot be diversified away. Okay, so the more you buy, it's going to stay there. And this part, we call it a market risk or the systematic risk. Systematic risk. Right? So if we would like to put all these things on a graph, then it's going to look like, if we have the risks on the vertical axis, okay, and the more you buy, then the risk is going to decrease. It doesn't allow me to draw a curve here. Okay, let's just draw it this way. Okay? It's going to decrease, but then it doesn't go to 0. Okay, so there will be a lower limit here of your effect of diversification. So this part in which you can diversify away is called the idiosyncratic risk. Okay, and this part, which you cannot diversify away, is called the systematic risk. Okay, so this is how we do the diversification, and we sort of prove it with a very simple mathematical model or mathematical example here. Although we have very extreme assumptions here, but the essence of diversification, or the logic and the rationale, follow. Okay, so there's the same if we have different stocks, which is different weights or different different standard deviations and different correlation coefficient, but the spirit follows, right? So the more you buy, and the more idiosyncratic risks you can diversify away, but then you're still subject to the systematic risk, which is by entering the market, then you're immediately exposed to the market here, and the market, you can sort of think of it as given or as exogenous. So there's no way you can effectively affect that. So that's given there. You cannot diversify it away. You're bearing that risk simply being inside the market. Okay, so take a look at the calculations, and you might be asked on the simplifications or the proof on diversification on the exams or problem sets. So take a look at the steps here and the crucial assumptions here, and try not to miss any of the terms during your calculations. I'll see you in the next video.